Today I am going to discuss about deadlocks. Okay, so what is actually deadlock means? So the deadlock, so actually a computer system have number of resources. Computer system have number of resources. Every process requires some resources to execute the system. So computer system number of resources, number of processes are there, but operating system smoothly allocate the resources to avoiding deadlocks. Actually, what is a deadlock means? System having less number of resources are there, more number of process for computing the task. So at this time, some process must waiting for some time because resource will be released by the other process. So how means suppose system having only 3 resources are there, but 5 processes are there. These 5 processes are may not compete for execution because some processes are waiting for getting a resource which is held by others also. So this situation is called as a deadlock. So system is sufficient deadlock when will arise a process cannot or a process cannot have enough resources for solving a task. If some resources are there waiting for some time because other process must finish the execution. So that's why the process may be moving into the deadlock state. But simply the computer system consists of number of resources, like a resource type called as a indication R1, R2, R3, and so on. These resources are called CPU cycles, memory space, IO device are resources. So each resource type has number of instances. Each resource type has number of instances, and actually in the all process before execution first requesting what number of resources are required. Before execution begins, a process requesting resources. After that, allocating the resources. After allocating, use the resources. After finishing the execution, release the resource. So this actually every process must follow this procedure. Before a process execution start to, it must requesting a resources. After getting a resources, use that, complete the execution of the above resources. After finishing the execution, release the resources. This concept is follow, or this principle follows request, use, release principles in the execution of a process. So this is the system model. Actually, deadlock system model simply nothing but a system having few number of resources are available and more number of computing processes are there. Each require certain amount of resources, but resources may not available. It waiting for some time. So this sometimes long wait time also means nothing but that's called deadlock situation. Suppose this deadlock situation arise in the when, for example, we are going to the roads for crossing a road by traffic signals. In the traffic, suppose for example, 3 or 4 roads are there. 3 or 4 roads are there. More number of people are crossing the road means if all people are came at a time, at once only all people are crossing the road means a traffic jam is there. So the traffic jam is nothing but a deadlock. Nobody cannot move into any other road because full stuck in the road. That situation is called as a deadlock. Like that, this type of situation arise the few number of resources are available, more number of processes are compete for execution, but operating system smoothly allocating the resources without deadlock solution. So this is the system model concept. A system consists of a number of resources. Each resource having number of instances are there, and every process must be before execution begins, request it, after execution, use it, release it. So this principle follows the request, use, release. But mainly, so what to say deadlock? Deadlock characterization. So or we will discuss deadlock characterization. These are the characterizing nothing but these are the deadlocks can arise if four conditions hold simultaneously. We say that deadlock will occur if all four conditions are occur simultaneously. The situation is called as a deadlock. Or simply, these are called a four necessary conditions for occurring a deadlock. First one is called mutual exclusion. So mutual exclusion, one of the characteristic of deadlock, what is called mutual exclusion? Only one process at a time can use a resource. Only one process at a time can use the resource. If one of the process was using the resource, the other process must waiting it. The other process must waiting it. So it is a actually mutual exclusion condition will occur in a non-shareable resources. Non-shareable resources. In the non-shareable resources, simply while the one process was going on execution, the other process must wait it. Or for example, a printer, while printer is printing is going on, the other process must wait it. After first process finish the printing, next process will take it. This is called mutual exclusion. Mutual exclusion is nothing but a only one process at a time can use a resource. Two or more process cannot be started simultaneously. This is called mutual exclusion. So mutual exclusion is useful in the non-shareable resources. For example, printer is a non-shareable resource because while the one process is printing going on, the other process must be waiting of it. After finishing the first process, then second process utilizing the printer resource. So this situation is called as a mutual exclusion. And the second necessary condition is called as a hold and wait. Hold and wait a process holding one resource and is waiting for one more additional resources which is held by other process. So this is called hold and wait condition. So what is a hold and wait condition? A process already holding some resource, and also to complete the execution, requesting one more resource which is already allocated by other process. So this situation is called as a hold and wait. Nothing but a one process, at least one resource is holding, but it will require one more resource, but that resource is available other process. This situation is called as a hold and wait. Hold and wait. Right? So can you understand the hold and wait condition? Because hold and wait, when we will say hold and wait means a process already having one resource, but it will require one more resource, but it is not available that resource which is held by other process. This situation is called as a hold and wait. And third condition, no preemption. Already preemption. So what is called preemption means? What is called preemption? A process holding a resource before early time preempt it. That is called preemption. But no preemption. Simply once a resource can be allocated to a process, after completing the execution only release the resources. In the middle, no way to release the resource. This is called as a no preemption. So no preemption is a process is only release the resource after completing the execution. In the middle, no way to release the resource. This situation is called as a no preemption. So no preemption means once resource allocated to a process, it only voluntarily release the resource, or otherwise until completion of the execution cannot be released. This situation is called as a no preemption. And last one is called circular wait condition. So circular wait condition is that there exists a set of process. For example, P1, P2, P3, and so on, Pn. Of waiting a process such that each process having a resource waiting for other resource. For example, P0 is waiting a resource which is held by P1. And P1 also waiting for a resource which is held by P2. Even P2 also holding a requesting a resource held by P3 also, like that. And P3 also waiting which is held by P0 also. Like that, it is called a circular wait condition. Circular shape. Suppose three processes are there, P1, P2, P3. For example, P1, P2, P, these three processes are there. Process P1 is waiting a resource which is held by P2, and P2 also waiting a resource which is held by P3. Even P3 also waiting a resource which is held by P1. This is called circular round, circular shape is there. That's why we call it, this situation is called as a circular wait condition. So these are the four conditions hold simultaneously. Then we say a deadlock has occurred. Yes, ma, are you understand deadlock characteristics? These characteristics are very, very important. What is meant by deadlock? Explain the deadlock characteristics are four necessary conditions. Are you able to understand deadlock characteristics? Yes, ma? Anybody?
Yes,
so these are the very, very important. So these four conditions simultaneously hold, we say that deadlock has occurred. So what is called mutual exclusion? Mutual exclusion. Yes, for mutual exclusion. While
only one thread.
One thread or one process. So one process was executing, the other process wait it. So this situation in the occur the non-shareable resources. So mutual understanding. Hold and wait, mathematics. What is called hold and wait? A process or thread already having one resource, but waiting for other resource which is held by other process. Means what it cannot, if you want to complete the execution, a process already holding one resource, so it will require one more also. That one more is available other process. They call hold and wait. A resource already holding, but it will require one more also. That called situation called hold and wait. No preemption, but only a resource will be released by voluntarily after finishing only. In the middle, no way to release the resource. The situation called as a no preemption. Circular way to a set of processes existing in a circular shape like a P1, P2, P3, and so on, Pn. It is a circular round, circular shape. Each process waiting held by other process, and more the second process waiting, third process like that is a circular shape. These 4 conditions simultaneously occur, we say deadlock occur. Yes, Mari, understand deadlock characteristics.
Yes, sir.
Yes, but deadlock characteristics are very, very important. Okay. So next one is the next concept to resource allocation graph. Actually, deadlock situation will representing the resource allocation graph. So you know already graph theory in the discrete mathematics. So what is a graph? A graph contains set of vertices and set of edges. So here a set of vertices V, edges E, and V is partition into two types is called a process and a resource. So vertices are partition two types. One is called a process, one is called a resource. The set consisting of all processes in the system, for example, P1, P2, P3, all a set consisting of all threads in the system, T1, T2, T3, like that. Resources are called R1, R2, and so on, consisting set of all resources in the system. So actually, before that, I have already said, yes, the computer system having number of resources and number of processes are competing for execution. So this, how many processes are there? How many resources are there? This resources process may represent in the graph theory, that is called resource allocation graph. For example, there are two, no, now you are understanding what is called vertices, what is called edges. So vertices is two types. One is called the process, one is called resource, and edges are requesting edge, assignment edge. For example, requesting edge, a directed edge, for example, TI to RJ. What is called TI is requesting a resource type RJ. So now you are understand here what is called requested edge. So the request edge is nothing but a directed edge. A directed edge TI to RJ. So thread to TI is requesting resource type RJ. And assignment edge is the directed edge where RJ to TI. Resource type RJ will be assigned to thread to TI. Here, thread or process. So PI to RJ, RJ to PI. So requesting edge. So what is called requesting edge? Process is requesting a resource PI to RJ, direct edge. Assignment edge RJ to PI, resource RJ will be holding a process or allocating a resource RJ to process PI. So this situation is we will represent it. See the next diagram. Yes, now here see the diagram. Actually, resource here three processes are three threads are there. T1, T2, T3. Here three threads are there. T1, T2, T3, and four resources are there. So the actually the thread or process indication circle, process or thread indication circle, rectangular shows the resource, and each resource contains number of instances. The instances represent dot symbol. Now you observe this diagram. Three threads are there. T1, T2, T3 are resource type R1, R2, R3, R4. But R1 contains one instance, R2 contains two instances, R3 one instance, and R4 three instances are there. So three. So now presently this situation is representing a resource allocation graph. Now you examine the graph. T1 holds instance of R2. T1 holds one instance of R2, and is waiting for an instance of R1, but R1 presently allocating to T2. Can you observe here? So T1 is a holding one instance of resource type R2 and is waiting for an instance of resource type R1. T2 also holds one instance of resource type R1 and one instance of R2 and is requesting to resource type R3, but R3 currently allocating to T3. Yes, ma, are you understand the graph? Yes, everybody? Yes, ma.
Yes, sir.
Are you understand the resource allocation graph? How to allocate the, already requested edge, for example, T1 to Ri edge called requested edge. But R2 to T1 is called assignment edge. Okay. So here requesting edge, assignment edge. So now here you observe the diagram, you observe the graph. So now T1 is holding a one instance of resource type R2 and requesting one instance of resource type R1, and T2 also holding one instance of resource type R1 and R2, two resources holding R1 R2 but requesting R3, but R3 is holding allocate to T3. Now T3 is resource type T3 will be assigned having the resource R3. So, but R4 is not allocating to any because it will not require R4 to any other process. So this is called a resource allocation graph. So here circles indicate the process, resources rectangle, but edges two types. So one is called requested edge, one is called assignment edge. Requesting edge is what TI to R1, but assignment R1 to T2 assignment edge. So right, so this is the resource allocation graph. Presently in the system, number of processes are there, number of processes are available, and number of resources available, number of each process, how many resources are requested, how many required. This situation is represented in the resource allocation graph. This situation is represented in the resource allocation graph. Now see the, yes, actually now for example slight modification of resource allocation graph. Actually why this graph used to this deadlock situation? If a graph contains a cycle, then deadlock may occur. If a graph contains a cycle, then deadlock may occur. Can observe this diagram or this graph. Now, for example, previous diagram is T3 requesting one more instance of resource type R2. So any cycle is there, you observe it here. Hello? Yes, ma, you observe the cycle in the graph theory. Hello?
Yes, sir.
So what is cycle? For example, start T1 to R1, R1 to T2, T2 to R3, R3 to T3, T3 to R2, R2 to T1. Now cycle is there. What is cycle means? Yes, well, cycle means what? Cycle is a closed loop, starting one vertex, visiting all vertices, ending the same vertex. Now you can start the T1. So you can go through cycle T1 to R1, R1 to T2, T2 to R3, R3 to T3, T3 to R2, R1. Right? Cycle is there. Are you observed or not, ma? Yes. Nobody cannot be responded. Yes. Nobody respond means why? Nothing but you are not listen, or otherwise you can't understand. Say yes or no.
Yes, sir.
Cycle, you observe one more cycle is there, one more cycle. So you start the T2, T2, R3, T3, R2, T2. Two cycles are there. So if
Yes, sir.
two cycles are there, right? Cycle is closed loop. Starting vertex, ending vertex are same. So here in this graph, in this resource allocation graph, two cycles are there. If a graph contains a cycle, deadlock may occur. So this is very, very important. So in the resource allocation graph will given, you will answer the a graph contains a deadlock or no deadlock. When to say deadlock occur, no deadlock means a graph after the situation. Presently, how many process, how many resources are allocated, this situation is represented the constructing a resource allocation graph. Then you detecting the resource allocation graph, a cycle is there or not. If cycle is there, graph may contains a deadlock, otherwise no deadlock, right? So see the one more. Sometimes, but that's why it is not actually cycle is a necessary condition, but not sufficient condition. But not sufficient condition. See this graph with a cycle, but here you observe this graph also actually thread T1 holding a resource type R2 and is requesting to resource R1, but R1 currently allocating to T2 and T3. R1 contains two instances are there. One instance allocated to T2, one instance allocating to the T3, but T1 is requested. T1 is requested. Now R2 also, resource type R2, two instances are there. One allocated to T1, one allocated to T4. T3 also waiting for resource R2. But now you observe this graph, a cycle is there. In this graph, cycle is there. T1 to R1, T3, T2, T1. Yes, what you say? A cycle is there. So here, yes, ma, can you observe this observation important? Can you observe here? So the previous graph, this graph you observe previous graph contains a cycle, but deadlock may occur. But this graph contains a cycle, but no deadlock. Why? You observe it here. A deadlock, a resource allocation graph with a cycle, but no deadlock. Why? So actually, you can observe here, if a graph contains no cycle, no deadlock. If a graph contains a cycle, if a graph, now this graph is cycle is there. If only one instance for resource type, only one instance, then deadlock is that. Every resource having only one instance, then deadlock occur. If several instances per resource type, possibly deadlock, but not a sufficient condition. Yes, you observe here. So because how means now you break the cycle. How to break? Actually, in this entire deadlock situation, every process must requesting, use it, release it. For example, thread T4 after executing a thread T4, it release the resource. After releasing resource type R2, it will connect. It will assign to the T3. Now break the cycle. Yes, observe. Yes, ma, observed here. Only one person responded. Remaining people are not. Remaining students are not responded. Yes. Nobody responded means you are not listening class. Yes, what you are observed previous graph, this graph, what you will observe? What you observed?
No cycles.
Previous cycle, but now here cycle is there. Cycle is there. But why deadlock no occur? What we say? Graph contains cycle, but no deadlock. Why means it is the resource the T4 after completing a T4 releasing the resource type R2. Now immediately allocating the R2 to R3. Now break the cycle. So this is called facts. These called, you remember, these are called facts. What is a fact? If a graph contains no cycle, no deadlock. Or second fact, if a graph contains a cycle, when situation only one instance per resource type deadlock occur, but several instances. Now here R2 two instance, R1 two instance, several instances are there, possibly deadlock. But now after completing the T4, no need for additional resource. That's why after completing, it will allocate the resource to R3, cycle breaking up. So this is very, very important. Resource allocation graph. What is meant by resource allocation graph? And find the deadlock situation. What is called cycle is there, deadlock. If single instance, but multiple instances, possible deadlock. But now this is the cycle is there, but no deadlock. Cycle is there, no deadlock. So this is the example of a resource. Now today class, we have learned deadlock definition, deadlock necessary conditions, and resource allocation graph. So this is very, very important question, resource allocation graph. So next one is now methods for handling deadlocks. Methods for handling deadlocks. So how to handling deadlocks when deadlock occurs? So ensure that system will never enter a deadlock state. So we must ensure that system will never enter into deadlock state. Then you employ one method called deadlock prevention, deadlock avoidance, deadlock prevention, deadlock avoidance, and one more method. This is called, one of the methods is called deadlock, either deadlock prevention or deadlock avoidance. System never deadlock state. Second one is called allow the system to enter a deadlock state and later recover it. First, allow the system to enter deadlock state and then recover it. Then third method, ignore the problem and pretend that deadlocks never occur in the system. Deadlocks never occur in the system. So these are the